In order to also further understand measurements, we need to talk about units. And so units are a known quantity of something. A dozen is a unit. It's 12 of something. A kilogram is a certain specific defined amount of mass. So a unit is a known quantity of something. And this is important because in science we need to compare results and ideas. I need to check your work. You need to check my work. And if we don't know exactly how much we're both doing, we can't replicate and do the same thing. If I just said, take some of this stuff and some of that stuff mixed together, it should turn green, and you go, okay, I'll take some of this, some of that mixed together, I got orange. We don't know if that's because something randomly happened or because I mixed too much of this and you mixed too much of that. There's two major unit systems that are used kind of globally. The first is the SI, which is an abbreviation of the French Système International, and this is also called the metric. This is the standard for math and science. It's what we're going to use in class here. It's used in most of the world. There's also the English and or imperial units, and this is what's used in the US, Liberia, and Myanmar. And just because of the kind of national cultural pull that the US has, it's also important to be at least vaguely aware of it. So that's where you've got feet, inches, pounds, etc. All right, fundamental units are the most basic ways to measure the universe. So these are things that if we don't have these, we can't do any other measurements. And there are 7 of them. First, we have length, which in SI is measured in meters. We have mass, which is measured in kilograms. We have time, which is measured in seconds. We have electric current, measured in amperes. We have temperature, which is measured in Kelvin. We have the amount of stuff, which is like dozens, measured in moles. And then we have the luminous intensity candela. So these are the fundamental units. Anything that you could possibly measure or want to measure about the universe is either measured in one of these units, measured in a unit that's related to this, right, meters versus feet, or it's measured in some combination of these units. So those are what we call derived units. Derived units combine the fundamental units. And here's a couple examples. Velocity is meters per second. How many meters are traveled every second? Density is kilograms per meters cubed. Atomic mass is kilograms per mole. And force is kilogram per meter per second squared. So anything that we want to measure, like I said, is either measured in fundamental units or a combination of fundamental units, or like I said, technically an alternate form, meters versus feet. And so that's what we talk about when we're talking about units and how to do that. As an interesting side note, if we go back to our fundamental units, all of these units are currently, like we are now officially, they are measured by fundamental constants of the universe, or things that we believe are completely unchanging. And this is important because if you said a meter is how long this stick is, and it's some fancy stick that you keep safe, well, if someone breaks that stick in half, then you don't know exactly how long the meter was. If they go in and they shave a little bit off, technically the meter has gotten shorter. That's why it's important that they're defined by fundamental constants, meaning there's some experiment that you can do that tells you, here's how long a meter is. You can go to your lab, you can set up the equipment, you can make your own meter stick. The last fundamental unit was the kilogram, and that was redefined in May of 2019, so just about 4 or 5 years ago. And so before they redefined it, the kilogram was technically, there's a platinum, I forgot what the other, it was an alloy, but there was literally a block of stuff that defined the kilogram. We said, this is how much a kilogram is this thing here. And that works until we need to start making copies of it, or until they found out that the copies were starting to change mass over time. And then you get worried, well, is the block that we had originally, is that changing mass? If it does change mass, how do we know if it changes mass, et cetera, et cetera. But now everything is defined. You can do an experiment. You can create in a lab what the thing is. And that's also important if we end up looking at records in 100,000 years. They go back to look at our science now. They may not use meters, but they can say, oh, here's how long a meter is. That's such and such Floerdal Schnarps that we use in the future, you know. So this is why we care about them being measured by fundamental basic constants. If you're curious about how they're actually defined, ask me in class and we can go over them.